Welcome back. So, we talked a minute ago about how we reduced the dimensions of R to make it easier to fit into memory. But sometimes even that still makes it difficult. So let's look at this algorithm here. So we're going to input graph G and parameter B beta. Directed graph G can have spider traps and dead ends, parameter beta. So the output, we want a PageRank vector R new. So we're going to set R old equal to 1 over n. That's our initial vector. We're just going to take whatever the number of web pages are and set it over. That's going to be our n, and 1 over n. And we're going to repeat until convergence. So the summation of R new minus R old is greater than epsilon, where epsilon is a really small value. All right. So for all j, rj new is equal to the summation of I through j of b beta times r old over the degree out. So r new is equal to 0 if degree of j is equal to 0. Now reinsert the leaked PageRank. So for all j, r new is equal to r new j plus 1 minus s over n, where s is equal to the summation of r new. Right? R old is equal to r new. This is kind of just an algorithm. So let's assume that we have enough RAM to fit R new into memory. Okay, so we would store R old and the matrix onto the hard drive, right? So we have to, this is where memory management is going to come into effect. All right, so we'll initialize R new is equal to 1 minus beta over n. For each I, so each of the degree out, or for each degree out, we're going to read into memory I, the degree out, the destinations, all the different destinations, and then R old. All right, for j is 1 through di. Okay, so R new destination is plus equal to R. So basically, we're going to sum beta old with R old over the new. All right. So we have R old. Let's look at R old. We're looking at the first selection, the first rank in the individual. So the source is, we're looking at web page 0. Web page 0 has a degree of 3, an out degree of 3. So, and it goes to web page 1, web page 5, and web page 6. So source 1 has a degree of 4. It goes to 17, web page 17, 64, 113, and 117. Web page 2 has a degree of 2. It goes out to 13 and 23. Okay. So as you can see, this color marking here, right? We're looking at R old. It's 0. It has a degree of 3, and it goes to 1, 5, and 6. Right? It affects those specific ranks. So assume that we have enough RAM to fit R new into memory. We can store R old and the matrix on the disk. For each iteration, we have read R old and M, write new back to the disk. The cost per iteration for this is 2 times the magnitude of R plus the magnitude of M. What if we could not even fit R new into memory? How would we approach it then? So this is a theory of linear algebra question, and it's a little bit to go on beyond the scope of this class. And with time constraints, I think we're going to move on for now and get into topic specific. So problems with PageRank. Measure generic popularity of a page. It will ignore and miss topic specific authorities, right? So this is what they're saying here is that, let's say that you want to know about basketball, right? And so you type in New York, or New York Knicks. Well, it may ignore the fact that you're looking at basketball and just bring up jerseys or something along those lines, because these marketing retail places have such huge uh, pointers to them, and it gives them a lot of rank. So uses their solution is topic specific page rank, and we're going to talk about that here in a minute. Used as a single measure of importance. Other models such use hubs and authority. Most commonly are hubs and authority. So it gives you weighted balances. And is susceptible to link spam. Artificial link topographies created in order to boost page ranks. And we talked about that before. Basically a bunch of links pointing to itself, or a bunch of pages that they've created to point to one page to give it a high ranking. And their solution is this thing called trust rank. So topic-specific PageRank is a random walker that has a small probability of teleporting at any step. Just like before, we had a probability teleporting at any step, okay? However, this one's a little bit different. So teleport can go to standard PageRank, any page with equal probability, right? So before, we could just go to any page in our set. Our set included all of the internet. But topic-specific PageRank has a topic-specific set of relevant pages. These relevant pages were relevant topics were hand put into categories. So these categories are specific, and we'll talk about that later, I believe. All right. Idea, the bias random walk. When a walker teleports, she picks from a set S. S contains only the pages that are relevant to the topic. So a specific open directory or a query of directories that are manually manipulated. For each teleport set S, we have a different vector RS, rank vector. To make this work, all we need is to update the teleportation part of the matrix formulation, right? So this is now a piecewise function, beta set mj. It's the same function as before, right? And S is our new n, because we only want the teleportation to be equal to the number that are inside our set. Our set now limits, and if it's not, then the rank is beta mj plus 0. So A stays stochastic. Basically, it doesn't give any of the pages that are not inside this category specific stuff a random teleportation probability. So you're not going to randomly teleport from a page inside the set to a page outside of the set. So, and A stays stochastic this way. We've weighted all the pages in the teleport set to S equally. Could also assign different weights to the pages. And compute the exact same way that we computed the original page rank. Multiply M, then add a vector, maintain sparseness. So let's take a look at this and how this actually works, right? So I have 4 web pages here. Node 1, Node 2, Node 3, Node 4. And we're going to say that our topic specific is only page 1, right? So beta being 0.8, right? And we're going to start off with a random node of 1 over n, right? So 1, 2, 3, 4, right? So after our first iteration, with beta being 0.8 and our set being 1, we're going to have 1 being our rank for page 1, 0.4, 0.1, 0.3, 0.2, so on and so forth. Now our stable is 0.294, 0.118, 0.327, 0.261. If we look at this, right, 1 goes to 2, 2 goes to 1, 1 goes to 3, 3 goes to 4. These, we would think that these are going to be naturally high, right? And that this would probably be pretty low. Okay, so let's look at this. So 1 is pretty high, and these are really high. Okay, but with this topic specific, one should be high, right? So now let's look at what happens when we set this ranked one and change our beta. So as we change our beta, we're we're the higher the beta is, the less the random teleport is. So higher betas means that we're going to have the smaller rank value for the topic specific. It's still going to be relatively high, but it's not going to be as high as if we change the random teleport value. So we should see if leaving beta or changing beta, leaving our set at 1, we should see as beta decreases an increase in the rank of page 1. So let's see, 0.17, 0.29, 0.39. So as you can see, our rank in page 1 goes up as beta changes, as beta goes down. Okay, so kind of an inverse relationship here. So now let's change our set, but leave beta constant and see what happens. So our set contains 1, 2, 3, and 4. So all the web pages are in there. Here's our, with beta being 0.8, we're going to see that, page 3 dominates. Okay, 1, 2, and 3. Beta 0.8, page 3 still dominates. Page 1 and 2, beta still dominates, but not by much anymore. Okay, and then 0.1, beta 3 still dominates, but we're starting to catch up. Okay, so we can see that the sets as the set gets larger, or as the set gets smaller, as the set gets smaller, we can see that the set that remains gets a higher value. This is how the topic specific keeps you, or brings authority to pages within a specific content. So if we're looking at basketball, we're looking at baseball, that would all be considered a sport. So under the category of sports or movies or entertainment, this is topic specific, so you'd be searching in specific topics and not getting authority pages like the White House inside your specific topic unless it pertains to your topic. So now just kind of randomly go through some link analysis in R to finish out the remainder of this video. So back when we first started, we talked about some things like closeness and betweenness and stuff like that, but I wanted to let you guys see some output from R. So what I did here is I used a library called SNA, and then we just created a test graph with 10 nodes that are randomly generated, right? And I had nothing to do with this. I used a lot of these slides from other places. So randomly generated, and we can also draw this graph if we need to. So if we take this generation right here and draw this graph, we have a wonderful looking graph that looks like this. And we can see that 10 is not connected to anything, right? So 10 is not connected to anything. It's independent. Okay. All right. So we're going to talk about degree, density, connectedness, betweenness, or centrality, egocentricity, and closeness. All of these we've talked about before except betweenness. So density is the number of existing edges divided by the number of possible ones, assuming no duplicates or loops. Okay. A graph with higher density is more strongly connected, and in general can better resist link failures. Okay, so if I want to get a general density, I can get, you'll see it's 0.4 here. So let's see, connectedness. Crackhart's connectedness for a digraph G is equal to the fraction of all DYADs, a group of two nodes, okay, U and V, such that there exists an undirected path from U to V in G. resistant to link failures. The R function for connectedness, right? It's going to check to say, is it connected? All right, and then it's going to say, of course, we're going to return false, right? Why is this graph not connected? Yeah, you guessed it. 10. There's no way to get from 2 to 10, right? So we want to know how connected is this, right? So it's what it does is it's going to take how many nodes is each one connected to. So let's see. Let's look at point 1. 1 is connected to 8 other nodes. 8. All right. How many other nodes are there? 9. 2 is connected to 8 other nodes. How many nodes are there? 9. So on and so forth. 10 is connected to how many other nodes? 0. How many nodes are there? Other nodes are there? 9. So we get a 0.8 connectedness. Okay. So can easily do this by hand if your structure is really small. But if your structure is not small, then we need to look into computing it. So betweenness or centrality, a measure of degree in which each given node lies in the shortest path between the nodes and the graph. For node V, graph G, betweenness centrality is defined as, yeah, that's really interesting, right? This is in the math course. Let's keep going. All right, a node has the highest betweenness if the shortest paths between many pairs of nodes in the graph pass through it. Thus, when a node with the highest betweenness fails, it is greater influence on the information flow in the network. Okay. Note that nodes 2, 7, 8, and 10 are not in any of the geodesics paths. Geodesics distance can be calculated using the geodist. So when we look at this, we can see there's an issue here, right? Infinite. It could be inferred that node 5 requires 2 hops to reach node 1, and node 10 is not reachable by any node, right? So we can see that it could be inferred that node 5 requires 2 hops to reach node 1. Yeah, so it takes 2 jumps to get to node 1, takes 3 jumps to get to node 3. And node 10 is not reachable by any other node. So that's why the distance is infinite, the betweenness. All right. Egocentric network of vertex V in a graph is defined as the subgraph of G induced by V and its neighbors. It can be computed metric over a local neighborhood, especially useful when dealing with large networks. As depicted in the figure, the egocentric network of 9 has 3 nodes, 6, 8, and has nodes 3, 6, and 8. So basically the nodes that are, another term for this in graph theory is known as adjacent nodes that are adjacent to it. Similarly, the ego net of 7 is only node 5. What's the ego node of 10? There are no adjacent matrices, so none, right? And the egocentric network for 1 is 2, 4, and 3. Okay. So let's look at the egocentric network for node 6 is 4 and 9. Note the subgraph extracted in the example 1, 2, and 3 respectively for 6, 4, and 9. So if we look at this, 6 is connected to 6, 0. 6 is connected to 4. 6 is connected to 9. And then 9 is connected to 6, but not 4, and not 9. And then 4 is connected to 6, but not 4, and not 9. Okay? Closeness centrality. We talked about closeness before. You guys know how to calculate closeness. Let's just see how it's done in R. So in R, we're going to take this same matrix here because we need to be able to get to all the points in order to calculate closeness. And we can see that the closeness for node 6, right, is 1, and the closeness for 4 is 2/3, and the closeness for 9 is also 2/3. So in summary, we introduced the idea of linking objects by relationship, talked about graph theory and how it visually can represent the structure of relational data, the applications of link analysis, Kleinberg hits, PageRank, viral marketing, law enforcement, and fraud. Do you have any questions? If you do, feel free to email me or see me in class. No, I think we just got an email saying that the rest of the semester will be over online. So I look forward to hearing from you. Send me an email, drop me an invite. Here are my references. All right, thank you.